Naoki visits us in Taiwan or for different occasions multiple times in the past years. But the last time he was here as a colloquial speaker was 15 years ago.
Maybe, yeah.
And probably, invited by Yenting.
Yeah, probably, I think.
So here comes the follow-up series of the advancement of the field 15 years later.
It is. Thank you. It's a nice introduction. Yes, indeed. Thank you. It is indeed my pleasure. This is my 5th or 6th times to visit Taipei, like over the past 20 years, and every time I enjoy, and now I feel like, really like I feel at home. And for me, it's close enough from Tokyo, so I perhaps I should come more and then enjoy the local food and so on. Okay, so let me start my talk, but with something for students. So, how many students actually? Not really. Okay, no, it's okay. No, it's okay. Yeah. I realize I'm now senior enough, so I want to tell some history. Typically senior people always talk about history. Okay. So about 30 years ago, I was a student, just like some of you. Okay. And this is, I'm showing the sort of evolution of astronomy in terms of the most distant object, which I call record redshift, okay? So back then, in late 90s, people were excited about redshift 5 quasars and redshift 4, 5 galaxies, and redshift 1 supernovae. Redshift 1 supernovae, this eventually led to this discovery of accelerating universe, okay? That was the state of the art back then, and then that was like this. And then some people, I remember my colleagues, my friends were even calling them like primeval galaxies and so on, okay? And back then, it was almost like imaginary or beyond the realistic scope to talk about redshift 10 galaxies and so on. But as you know, as a real astronomer, you know the development afterwards, even up to 2020. So nowadays, it's like a daily routine to talk about redshift 10 galaxies, redshift 9 gamma ray bursts, redshift 7, 8 quasars, high redshift supernovae, even like distant gravitational wave sources. So this is impressive, okay? And of course, this is now extending even beyond. Now, so this is for you students, okay? You recall, this is the take-home message for you today. Okay, this is already, I can end this talk and here, okay? This is, remember, like, when you are students now, this is a record redshift, like redshift 14 galaxy and so on. But then you still have a huge discovery place, I hope, just like I experienced in the past 10, 20 years. So just the question is, what are these most distant objects in the next 10 and 20 years? You might wonder, okay, so I plot this up to redshift 100, and then this the year 2040, 2070, when I celebrate my 100th birthday or so, and even the next century or so. So I'm sure astronomy develops in this way, and please remember for your today's talk that, this year some guy came from Japan talking about this low redshift object for you. Good. Maybe there are no objects at redshift 100, but still we are sure there will be hydrogen gas that will be the target of next generation radio astronomy. That is my main topic today. Okay, just an introductory part. Many of you, or most of you know the success of lambda CDM. Here, I show the success in terms of the mass scale from galaxies to galaxy clusters to even larger object, large scale structure, and then the beautiful consistency or match to the observed mass spectrum or observationally inferred mass spectrum and the lambda CDM prediction. Okay, so this is pretty much satisfying. Okay. But let me still put a small question mark. Actually, I should put here. like this. Unfortunately, we are not really satisfied with this success. Why? Because we have been able to prove only down to the galaxy scale for small font. Sorry, this is like 10 to the 12, like Milky Way galaxies. Down to Milky Way galaxies size and mass, the observations and our theory standard model is consistent, but we never know what's happening or what is the real fluctuation amplitude or mass spectrum beyond or below the galactic scale. Okay, that is kind of can be a final test or check of the standard model. Okay, so in fact, even with the currently available observational proofs like galaxy clustering, Lyme alpha 4s, or even the UV luminosity function of distant galaxies, we can only place loose constraints down to here. So here now, instead of a mass spectrum, I now plot the power spectrum at the relevant length scales. Okay. And then there is this region is essentially like left uncertain. Naively, we expect this mass spectrum or fluctuation amplitude goes maybe like a simple power law, but we know, at least observationally, we really don't have any idea. And interestingly, this one of this recent paper by Esteban et al., the analysis of Milky Way dwarfs even points to the slightly enhanced small-scale power. That's interesting. Well, observations come with a mixture of this uncertainty or level of the fluctuations. Okay, this is a fine image of a strong lensing system, and by some nice analysis, we can say, well, you know, the underlying mass distribution can be either like smooth down below the galactic scale, or like maybe clumpy, and the analysis result is just a mixture or confusing. Some portions maybe we prefer more clumpy structure in the lens galaxies, or maybe smooth distribution. My colleagues in Osaka, he's trying to prove or detect the anomaly in this radio lensing, and then to prove the substructure abundance and so on. The previous paper by Esteban, he analyzed the internal structure of dwarf galaxies compared to the naive prediction from standard CDM model. And then some of the small dwarf galaxies might indicate the excess clustering or even like more small scale structure down to this mass scale. So this is interesting. Okay. And another proof might be available through the exploration of the high redshift universe by, say, for example, this famous picture by James Webb Space Telescope capturing one of the most distant galaxy. As you know, James Webb has been very fantastic, finding many objects at redshift 10 and beyond. This is interesting. So this news or the story might be already a little bit dated, but there continues we continue to observe like discovery or like reports saying, well, there are many indeed bright massive galaxies in the early epoch, redshift 7, redshift 9, and so on. And back, say, 2 years ago or so, people argued, well, this abundance or existence cannot be really explained by the standard lambda CDM unless we invoke like extremely large star formation efficiency and so on. And largely this kind of mystery or problems is kind of like evaporated because, you know, some of the object turned out to be low redshift interlooper or so, but still kind of ongoing. Why we find actively star-forming galaxies or even massive black holes in the early universe more than just expected naively from the standard model. And this paper just indicates maybe, you know, available or future 21 centimeter radio emission can help understand the evolution of galaxy population and star formation activity. Okay? Good. So back to them. Then theoretically, so I wondered, you know, this is still introductory part, but I just want to show you how sensitive it is to the structure formation on the assumed power spectrum on subgalactic scales. Okay, so here as a theorist, I just thought, oh, maybe there is like a turnaround of this mass or density fluctuations to a bluer portion, like what we usually call blue tilted power spectrum. And there is no worry. Theoretically, there are more than a handful of ways to produce this kind of density fluctuations from physics of inflation, from physics of dark matter, or some other effects. Okay, even like, one can invoke even like primordial black holes or so. So it's nice to test what happens if the power spectrum is enhanced or blue tilted. This is a result. It's a simple n-body calculations that we did with my young colleague Hibano. So this is a typical standard lambda CDM model, okay, redshift 9 density distribution with slightly enhanced power at subgalactic scales. We see more structure developed. With more enhanced power spectrum, then we see clear large scale clustering plus the clumpy features in individual galaxies, just like we observe by the JWST observation. So this might be indicating something. Instead of seeing by density distribution, if we plot the abundance of galaxies, dark matter halos in this case, it's pretty clear that only a small enhancement of the primordial power changes this overall looking very much. Okay. And again, this is still within the uncertainty range that we have in the available observations. Okay? My thing is that by changing that portion, we still keep the success of the lambda CDM at large scale. So this is present day mass function, halo mass function from galaxies to clusters. We do not ruin the success, but by changing this power amplitude, we can dramatically change the abundance of galaxies at redshift 9 to 7 or so. So this is one way to think about. Maybe recent observations, they are pointing to the modification or change of the power slope at subgalactic length scales. Okay?
Do you have a cutoff? Do you have a cutoff at some case?
No, it's a very simple motivator. So here there is like a pivot point, and then we put some straight power. This is a hard case, and soft case is just in between. Like this. Yeah, one can do like slow, like blue running or so, but the result is essentially the same. Good. All right, let me skip this. This is the same thing. I just want to say one thing. Listen, this kind of simple test, not because we are motivated, we are like easygoing guys. We have been like pursuing this possibility over already 10 years with David Sparger, and we wanted to make theoretical predictions and what happens if we modify the small scale power. So this is one manifestation, and I want to believe that I'm not like really an easygoing guy, and when somebody says something, I go for it. It's not like that. I have been doing this for over 10 years. That's what I want to say with this slide. Okay. Now this is one extreme example. If we change the small scale power, the formation process of the first generation stars and the black hole formation, the supernova explosions like Ken Chen is doing, it's dramatically different. We can even expect the formation of first stars at redshift 300 or so in this extreme case. But still the physics of star formation is the same, so one can make a sort of a reliable prediction on the abundance and the distribution of these luminous objects at very high redshift. So remember the redshift record. If we stick to the standard model, we do not expect the luminous object at redshift 100. But this pretty much depends on the assumed cosmological model and density fluctuations. Okay, we can also prove the star cluster formation. In this case, we just do simulations for the standard model, but we can still predict subgalactic objects forming very high redshift. This is the work, collaboration work with UCLA group, and together with them we produce continuously these papers on formation process of star clusters like this. And then we say, this is from one of the press releases, okay, the abundance of bright galaxies and star clusters can put some tests on the physics of dark matter, physics inflation, and so on. Okay, this is from my thing. All right. If you are interested in the supermassive black holes and you wonder about the origins of them, it's also related to this first generation object, especially when the seed black holes were formed. Once we generate or we form seed black holes, then we can follow this famous Riss diagram. There are multiple ways for the seeds to grow to be supermassive black holes, like starting from population-free star remnant, or the currently popular supermassive star again can change working, I think, and then through the runaway collapse of dense clusters and so on. So all of these can help understand how the structure developed in the early universe. And of course, recent observation is really, in this sense, encouraging detecting more and more abundant massive black holes in the early universe. Good. Gravitational wave, it's currently proving a relatively local portion, but the third generation experiments like planned Cosmic Explorer or Einstein telescope, it's gonna be spectacular. Wherever in the universe two black holes merge, let's see, the horizon of these experiments, 30 solar mass, 30 solar mass black hole mergers, wherever it happens within this universe, say up to redshift 50 or so, we can see it, or we can hear the sound of this gravitational wave. So in the future, wherever it happens, and I'm sure it happens, then we can kind of detect this signal by this planned third generation gravitational wave experiment. So the next 10 years will be, in terms of this redshift frontier exploration, it is very, very interesting, and I expect many surprises coming from gravitational wave and some other experiments. So yeah, this is just the end of the introductory part. There is a huge discovery space, and I hope we together continue exploring distant universe. Okay? And then I like this diagram. There are many interesting topics like supermassive black holes, density fluctuations, inflation, dark matter, and so on. And the formation of the first stars and the mysterious cosmic dark ages, they really have the key to understanding many of these things, like from gravitational wave, Big Bang nucleosynthesis, reionization, and so on. Okay? So this is the main topic today. What was happening in the cosmic dark ages? Okay? We have a good hope. Now the square kilometer array is under active construction. This is a big project with 16 countries plus African partner. It's next year coming soon, at least in some partial operation next year coming soon. The first stage operation will be with hundreds of thousands antennae in West Australia and South Africa. It's enormous that once it comes online, then the raw data traffic will be a few exabytes per day. It's amazing. It's like more than comparable to the current data traffic in internet. Remember, it's a nice rule of thumb. For 1 exabyte YouTube movie, it takes 200,000 years to watch for you. Your son, your daughter, you say, well, don't watch YouTube more than 30 minutes, but to see 1 exabyte, it takes 200,000 years. Okay, and then SKA produced raw data of 3 times per day. That's amazing. So this will be your emergent task for data science and machine learning applications, AI and so on, because we do not even know which data to be stored. But the information comes from the sky and it collects the data and we need to analyze. So this is a big, big challenge, like a human endeavor to get the meaningful data, okay? But this is typical of interferometer. Today, the latter part of my talk, I focus on more slightly or a little simpler experiments called 21 centimeter global signal. And in fact, many people share this feeling. You know, there are many ongoing projects like EDGES. We heard about the first result, okay, by EDGES. There's SARAS. So people typically place a simple radio telescope on the desert, on the lake, or any like remote places. There are many, many such projects ongoing and planned. Okay. All of these are aimed at detecting the global signal. Global signal is the sky average, all sky averaged radiation temperature at a particular frequency. Okay, mostly coming from the early universe. Okay, planned and under development, China's Sigma and the international, I think, Antarctic experiments. I always wonder why my colleague astronomers like you tend to go to remote places, like in the middle of China, in the middle of nowhere in China and Antarctic and so on. This is always many of you like, why can't we do this experiment right in this Taipei or so? But it's impossible to because of radio interference. Okay. Well, anyway, a huge effort is being put in to these kind of experiments to prove the signal. Okay, so this is a typical brightness temperature evolution as a function of redshift. So from now on we aim at detecting the hydrogen 21 centimeter signal, and then for this plot one can easily calculate this brightness temperature variation like this. There are corresponding physical processes, but I explain this later. So once we can detect this signal by any of these experiments, one can do cosmology, one can get physics of galaxy formation, or even one can get the physics of dark matter and so on. Right? Okay, one good surprise that I was also surprised. Basically, we want to measure the temperature. Brightness temperature, or for this case, spin temperature, in the same way. But for CMB, the temperature evolution is very, very simple, as you know, from redshift 1100 to present day. You know, everybody knows and everybody can calculate. Even a high school student can calculate this CMB temperature as a function of redshift. You can let your son or daughter to remember this formula, and he or she can calculate it quite easily. For some reasons, 21 centimeter spin temperature, it should be like a cosmological proof. It's very hard. I don't know why. For CMB, it's easy enough. Well, 21 centimeter spin temperature is determined by the weighted sum of radiation temperature, that's CMB for us, and the gas temperature. And so essentially it goes somewhere between this radiation and gas temperature. The definition is like this. It's just you imagine a mean molecular weight. It's the weighted mean of this. Well, there is a physical coupling coefficient here. You know, it depends on the collision strength and the coupling through Lyme alpha photons and so on. And then to observe or to interpret, we actually use this brightness temperature. It's essentially the difference between the spin temperature and the CMB temperature. And the spin temperature is just a level population of the hydrogen ground state. More classically, it's like a electron spin up and down, or spin parallel or anti-parallel with the nuclei. Okay? And then this optical depth part, we can calculate in this way with some velocity effect and so on. But these are like physical constant. And as usual, we can do, this part is just tau for small tau, and for large tau, it's just 1. So should be simple enough. But when there are density fluctuations, it turns out it's very, very complicated. And then it turned out, at least for us, we needed supercomputers and a series of big calculations to get the accurate spin temperature that I show you today one by one. All right. One other complication is this: in the early universe, baryons do not place the dark matter distribution, okay, because of baryon acoustic oscillations. So effectively, baryons were, after recombination, baryons were moving at supersonic velocities in the underlying gravitational potential well of dark matter. This complicates things. So at large scales of, say, in this case, 500 megaparsec, we see this density fluctuation, just like CMB fluctuations. But velocity space, it's more involved or complicated. But this is a direct kind of prediction of it, because we now already observe like these Doppler peaks of CMB, so there must have been these sound motions in the early universe. Okay, so one typical effect is because of these supersonic motions of baryons, typically a few to 10 kilometers per second at high redshift, the gas distribution is reduced, or the density fluctuations of the gas is reduced with respect to the dark matter density fluctuation. So this is the dimensionless power amplitude for dark matter and the corresponding power spectrum of the gas distribution at the relevant small length scales. Okay. Of course, this motion, because if we want to observe radio at the particular frequency, of course it's affected by the relative motion of the gas, which we call redshift space distortion. It's not just the cosmic expansion, but the local peculiar velocity and the peculiar velocity gradient. You can imagine this is like 21 centimeter, like sharp line, so it's essentially a line transfer problem. So we need to take into account this velocity, local velocity gradient as well. Okay, so including all of these in the growing small scale structure is very hard. But let's go one by one. Okay, here, okay, I think I need to take care of. I don't know. Let me see. You can be a timekeeper actually.
Sure. Yeah.
Okay. Anyway, because once I start speaking, I never stop. All right. Here, the simplest one, gas temperature. Okay. So we start from redshift 200. The universe is relatively smooth and homogeneous, so no surprise, the gas temperature is now like around 300 Kelvin. This is a small box simulation, 3 megaparsec, and then we include all important things like chemistry and Thomson heating and so on. Okay, let's move on. Like this. Eventually you see the development of structure and gas temperature, like this. At least, let's see, below 20, these are like collapsed, virialized small mass mini halos, and we have high temperature. Okay? Move on to the next. Now this is, here I show the spin temperature, but the spin temperature minus CMB, so effectively like brightness temperature if we observe in radio. Starting from this blue, like slightly negative temperature, but looks like this. You see now these high density regions, because of more strong collisions in the gas, we have a larger spin temperature than CMB, whereas the other parts are pretty much similar to the CMB temperature. But before, the whole region was showing a negative sign because the CMB temperature is now higher than the gas temperature. Okay, so this kind of nonlinear transition or nonlinear swap of spin temperature can happen because of the dependence of the coupling constant on the gas density. Okay? Next. So, as I explained in the beginning, okay, the spin temperature is a weighted sum, so it should be somewhere in between radiation and the gas temperature. Well, however, the gas density drops much faster in this plot as a function of redshift. So initially, the spin temperature is coupled to the gas temperature, but as the gas gets less and less dense, the coupling is lost, and then the spin temperature is coupled toward radiation temperature again. This is what's happening. Okay? Now, even more complicated. Okay, for the homogeneous case, we have like omega baryon, omega matter, and so on, expansion history. It's fairly easy to calculate the spin temperature evolution. It's a small piece of code. Okay, we can easily get download. But there should be a collection on it because of nonlinear clustering. Here I show the local spin temperature with respect to the homogeneous case. Okay, so here already redshift 200, we have slightly less spin temperature, and here in this region already excess spin temperature. And this evolution is very complicated. Yeah, did you see that? The blue and the red portion has been swapped at some point. You see that? It's the high density region is not always hotter part in terms of spin temperature, and I explain why. Okay, this is like unusual technical detail for colloquium, but since this is a newly discovered effect, let me try to explain. Okay? So redshift 100, this is a gas distribution in the real universe with some overdensity, with some underdensity. Nearly cancels, but because of nonlinear clustering, it does not perfectly cancel out. Okay? So this is the mean density, homogeneous case. This is the spin temperature for the homogeneous case. So of course, the mean part has the same density and same temperature. Okay? However, slightly high density part, slightly lower density part, it behaves differently. Again, the spin temperature is the weighted sum between the radiation temperature and the gas temperature. So things like this. Here, the denser part looks relatively bright. The low density part relatively less bright. Something happens at redshift 70 or 65 or so. Now you see this smiley feature. Again, less dense part and high density part. Now it's kind of canceling. However, both have positive signal. Okay. Once again, here this is a weighted sum between TCMB and the gas temperature. Here, the same thing between CMB temperature and gas temperature, but the collision strength is different. It turns out that around this redshift, all of the gas shows a positive signal, just like you see here, compared to the completely homogeneous case. All right, redshift below 60, the opposite thing happens. Now the high density part is more strongly coupled to the gas that has a lower temperature than CMB. Okay, you can laugh at me anytime. Okay, but low density gas is more coupled to the radiation temperature. Then this radiation swaps. High density part looks colder, whereas the low density part looks brighter or hotter. This is the effect we haven't known yet before this work. Okay, so and in the end, it's like the end point is simple. Like only this high density part is very hot and so. Okay, now this is, I remind you, this is like a 3 megaparsec box simulation. We need very high resolution. But the global signal, we need like a gigaparsec volume. So we need to deal with that. So in the end, we decided, we run bunch of simulations with different density, different velocity, and so on. And we produce this spin temperature evolution as a function of local velocity, as a function of local overdensity, and so on. And we integrate over it. Like this. This is a simulation suite we run using expensive supercomputers and do this gravity hydrochemistry calculations to get very accurate spin temperature. And overall structure looks the same. This is, spanning from -3, -2, -1. This is underdense regions, overdense regions, and as a function of relative streaming motions, as I explained. And then we generate this large simulation grid. So you can imagine individual part is the small box simulation I showed you. And then we can get the cosmological signal, the resulting plot. This is only one main plot from our Nature Astronomy paper showing the frequency modulation of the spin or 21 centimeter global signal from redshift 100 to 30 or so. Okay, so I do not repeat my explanation, but now I hope you're following me. Above let's say 70 at the relative level compared to the homogeneous case, we see more signal from 21 centimeter. There's a turning point at around let's say 70 for our standard model, and then this temperature decreases again down to let's say 30 or so, and this modulation level is about 1 millikelvin. Okay. 1 millikelvin sounds small, but if you're a radio astronomer, it's not desperately small. So signal-wise, perhaps we can detect. The real problem would be like foreground removal and calibration and so on. But 1 millikelvin is not something we give up or like we forget about it. Okay. Now I just explain the same thing, but this is a very physical effect. No exotic thing about, say, nature of dark matter and so on. We only assume there was small-scale clustering, just as predicted by the standard lambda CDM model. Very good. Let's skip space distortion. What if the power spectrum is not standard? What if the dark matter is warm, slightly lighter particles? Then this effect is different because of the difference in the gas clumping in this way. Now here I directly compare the case with CDM on the warm dark matter. The difference is only in the small scale power amplitude. Now this modulation is different. So if we can detect this modulation with high statistical significance, we can measure the mass of dark matter particles in almost a direct way. Okay, very good. And for that, we run another set of same simulations for warm dark matter and different particle mass. This is like particle mass 2 kiloelectron volt, 7 kiloelectron volt, and 25 kiloelectron volt for assuming standard thermal radicals. Okay, now the observational part. Okay, now I'm a happy enough guy being a theorist doing computer simulations. But how to prove this? Okay. Unfortunately or interestingly, the sky below 30 megahertz, that's the target frequency, is largely unknown actually because of the Earth's ionosphere. Ionosphere almost either completely block or scatter this outer long wavelengths radio waves. You see this transmission plot. Above, say, 20 meter wavelengths, we can't see anything from the universe if we stick to be on the ground. Okay, So we need to go to the moon. Okay, this is a very good reason to go to the moon, because these experiments we can only do on the moon, preferably on the back side of the moon. And of course, some countries already appreciate this and started thinking, oh, there will be a nice opportunity for radio astronomy. Maybe, I think this is like US something, like, maybe one can make use of lunar crater on the backside. There are many craters on the backside. China proposes this, lunar orbit satellites, including these daughter satellites, to measure this signal. It's a clever way, because even for the moon, landing or placing these objects is very difficult. Just like energy-wise, you need to carry away or evaporate the gravitational energy in some way. But putting it into the orbit, I'm pretty sure with the current technique one can do. I don't know. China, US, even Japan, and so on. Many countries can do. And Japan has its own project called Tsukuyomi. Again, placing the radio telescope. It's essentially, kind of dipole antenna maybe. Like, my laundry rod something. Then if we place like 5-meter laundry rod and do the fine calibration, we can get this signal. Okay, a simple forecast, if we place a single antenna on the backside of the moon, observe 1,000 hours, this thermal noise, sky noise, is just like this. So we can, with this integration, we can get maybe the deepest, coldest part of this signal. If we have 100,000 hours, or equivalently, if we place 100 antennae, the noise level gets down to this. So possibly we can even see this hotter part as a function of redshift. This is as a function of frequency, of course. And if there were some luminous object emitting Lyme alpha photons, then the situation gets much, much better dramatically, because the signal is boosted by Lyme alpha coupling. And then we see all of these curves with a simple experiment. Okay, the same thing essentially. And then, as I mentioned, we do have this kind of cosmological volume simulation, so we can make the clustering. That maybe one can do with SKA. The clustering of 21 centimeter intensity, redshift 20, 30, and 40, and this difference in the curve of the same color is difference between the CDM standard model and warm dark matter. Okay, it's small, about like 10% or up to 20% level, but depending on the exact nature of dark matter and the exact power amplitude, we can do this measurement even in the next generation 21 centimeter experiment. And similarly, if we have the signal boost by Lyme alpha photons, then we get the amplitude itself quite easily by the proposed experiments. Okay? The same thing, it's just showing the evolution of the power amplitude for fixed K. So if we can prove this power amplitude evolution as a function of redshift with SKA, for example, then we can pinpoint the fluctuation amplitude, namely the nature of dark matter. Good. So I'm now proposing in the not in a very distant future, but within 10-15 years time scale, we do both interferometer and we do also the global signal experiments on the backside or lunar orbit. Then we can get this information. That's it. Okay. So I don't know. Okay. Good. So to summarize, for the first time, theoretically, we performed a very accurate 21 centimeter signal, accounting for nonlinear clumping, baryon dark matter streaming motions, and redshift space distortion. So the result I showed today is currently the best accurate calculations, including unknown effect. Okay. Nominally, it's about 10% effect, both global signal and the power amplitude, the clustering amplitude. But it's kind of within reach of proposed experiments. Okay, and today I focus on dark ages when supposedly there is no luminous object, but afterwards cosmic dawn and epoch of reionization. More astrophysical modeling is complicated, but once they are under control, then we can get much larger signal. Maybe we can even hope to isolate the cosmological signal just I explained today. So yeah, let's have a good hope and then let's propose moon missions and so on. Okay, that's the end of my story. Thank you very much.
Questions?
Naoki, thanks very much for a very wonderful talk. And I have more like a comment on this, you're tilting the small scale power spectrum. Try to resolve the enhanced star formation of excess UV luminosity at the high Z observed by JWST.
Yeah.
But I think the first question is about what the physics behind the small scale power spectrum will be tilted.
Oh, okay.
The second question is actually, I think this problem can be probably also resolved if you just boost your simulation by a factor of 100, 10 to 100. The reason is you think about a TNG simulation. So they present the same box size with a different resolution. You can definitely see very high resolution case. They form more halo and small scale structure. Just purely they increase the resolution for the dark matter and barrier. Which enhance the clustering also at the earlier times, enhance the star formation. And also other physics, probably you heard also like feedback tree models and the top heavy ion models also can also try to release the tension for this observational result. So that's I think probably if you have enough supercomputer time, try to do a higher resolution. Maybe to see how much the difference. But I would like to hear about more like what's the physics back up for the tilting the small scale power spectrum.
In fact, there are many large enough flexibility for the modeling part. Some of your colleagues are working on that, like physics of inflation, like some change in inflaton potential, or adding carbon, or running mass, or action-like models, or primordial black holes, and so on. These have been already discussed or proposed even before these observations. So, in general, either enhancing or even like red tilt or suppressing small scale power, I don't think it's easy, but there are many possible mechanisms to achieve it. The second part, it's usual choice kind of or argument, if this is like cosmological or fundamental physics part or complication in astrophysics like star formation activity, feedback and so on. But we do not need to stick this like fresh news 2 years ago, but to me, bringing the star formation efficiency to the maximum or like feedback free despite formation massive stars and so on is really extreme. So it's for me it's like a choice of going extreme astrophysics or going slightly exotic early universe physics and so on. But definitely we should keep exploring both ways. But hopefully future observations will tell us which one is correct, or if the primordial power spectrum is really straight line or enhanced or suppressed. Okay?
Thank you.
So any implication or really constraint from the degree of ionization in the gas?
Oh.
So the optical depth.
Oh, okay. Yeah.
10% maybe not really.
Good point. The trouble is, in fact, if we allow more star formation or more than expected, then we start wondering, well, there's a like Thomson scattering optical depth constraint. But that part I'm actually exploring separately. So if you believe Planck result of optical depth 0.06 or so, this kind of model is starts touching. But as we explored, actually this is the skipped part. As long as the galaxy luminosity function, we can keep things complicated through the effective mass to light ratio. Okay, this is the first thing. Now, so with this model, we do not really violate the ionization constraint. Second, in the CMB analysis, there are some papers indicating some large-scale kind of anomaly or peculiarity in Planck. So if you use Planck data only above L of 20, the optical depth constraint is like even like 0.08 or so, much loosened. So I don't think Planck result is incorrect, but if there is some reason, maybe only local in our Milky Way or local environment, and if we exclude the large-scale CMB information, then optical depth constraint is somewhat closer to naively we can expect. This is interesting, actually. Yeah, but in short, you're right. If we do the boost or the blue tilt too much, then eventually these ionizing photons can be produced too much. So we need to think about different ways. Yep. Amen.
Thank you for talk. I have just one follow-up question. So, by changing the small scale power spectrum, I wonder then. I suppose you will change the galaxy formation.
Yeah.
Lower ratios.
Oh yeah. In detail, yes. Yeah. Formation history is changed. Stellar populations tend to be older, but that's exactly some JWST result is telling us, like, oh, distant galaxies, they already have like old stellar population, and what happens and so on. Yeah. So I think this argument continues. Like it's my bet or prediction. We never settle this argument. Like
Sorry, I have a second question.
Yeah.
So for the 21 centimeter prediction from your simulation.
Yeah.
So so there's like a previous people do theoretical calculation, and it shows that it's actually sort of fainter, low ratio 100, but here you are showing it's brighter, 100. So like is it like just because they previous study they did not consider the physical effect you mentioned? So actually the prediction now is entirely flipped. We need a very high resolution hydro simulations with relevant physics. That's it. So we really need to prove even below the mini halo scale this clustering. Remember this is 3 megaparsec. And the thing is like this existence of say mildly overdense regions. This really controls the overall signal. And unless you really resolve this part, we can't get this like the smooth modulation. That's the trick. And with my colleagues, we tried hard to explain, like using like a halo approach and so on, but it's very difficult. This is like if in the large scale structure, it's like a nonlinear filament regime. It turns out these filaments are really contributing at this scale. So that's it. Yeah.
So now, are you in your plots? Are you showing the delta with respect to the homogeneous case?
Yes.
Right. So I guess what Tim was thinking is with respect to the CMB. So this is a delta.
Yeah. Sure. In always a relative sense.
Yeah.
But, yeah.
So I have a question about the late time behavior. Because you mentioned potential effect on Lyman alpha.
Yes.
And I guess that happened at the late time.
Yep.
And the question is, because you get stronger signal, but the question is, should you decouple the two effects? Are you constraining dark matter or actually the production of Lyman alpha?
Very good question. These are all like variant, the CDM and variant mode, variant warm dark models, and very likely degenerated with other effect. However, the strength is we can predict, or observations can tell us this modulation or the temperature as a function of frequency. So you're familiar with. Even if the noise or the uncertainty is large, if we have like 50 or 100 points, the statistical significance can be increased. I can easily imagine this difference between CDM and warm dark matter. Even with this large error bars, integrated over large frequency range, we can get statistical answer, just like you're familiar with. So that's my hope. And then, the Lime alpha or star formation and so on, they should have a different frequency dependence. So
should have smooth pressure evolution.
probably, probably, yes, yeah, yes, okay.
So I also have the question for this 21 centimeter pulse. So, for example, in this plot, when Z goes below to 70, the brightness temperature start to drop.
Yes.
And until the ratio to 30, roughly the first stars
Exactly.
start to form.
Exactly.
So the key question is here, because the mention you explained is due to the dense part was start to couple with the gas. And gas have a lower temperature. But however, when low dense gas go into structure, they will heat up. So how this heating have been considered in the simulation? Or visualized heating or filament formation, like a mini halo formation? Yeah.
Good. In this case, we took very simplified case. Right? We assume like a free coupled regime. Like this is assuming effectively the whole volume is flooded with Lime alpha. That's it. In reality, as you say, let's take one standard case. There must be at redshift 17 or so. There must be first star forming and emitting radiation and so on. But this local effect is not that important actually, because the relative volume is small. All we care is the amount of Lime alpha radiation sourced by these newly born stars, and then that one can maybe parameterize in a nice way. And in the end, we want to get the global signal out of like gigaparsec volume. So it doesn't matter, okay, here's like one star forming region, one star forming region. Volume wise, it doesn't really matter. The effect of Lime alpha photons, like diffusing out from these regions. But of course, in our case, it's very, very simplified. Yeah.
You see, it's a pretty complicated process.
It is.
Yeah.
It is. But
although the volume filling is small, but the dominant is still dominant
the radiation source, yes.
very large. Yes.
So maybe cosmic dome might be a good hope actually. Yeah.
Thanks.
Yeah.
That's great discussion already. Any final comments and questions? I have one. So this inhomogeneity effect sounds like you should put your name on it.
You should put your
How are you going to code this effect? Because you have a catchy name for this inhomogeneity.
Yeah. Oh, you can remember this is I show this. I believe this is the brightness temperature, but the underlying density and velocity field is completely different.
Yeah.
Remember? So and it's not very easy to simulate the whole box
Yes.
at once.
Yes. So
Yeah.
my comment is that this effect deserves a name. The distortion on top of the homogeneous.
Yeah.
Otherwise, then we will hear about claims on the new type of dark matter models and
Right. Okay. Now I get your point. Yes. Yeah. Like myself, I worked on like annihilating dark matter, decaying dark matter, and so on. That's completely different thing. This is the signal we expect even for the standard like cold dark matter. Yeah. That's sort of like a real physical effect. Although, it depends on to whom you talk to, like, Yeah, that's a good point. Yes.
Okay. With that, let's thanks Naoki.
Thank you.
We'll be around till
Friday. Yes.
So